So now the next pending blocks are basically this amplifier and the DAC. And for that, first let's understand how you will be implementing both of them. Right? We don't know how circuit level implementation of these are going to look like. So let's first do that. And in particular, let's focus on the implementation for a Flash ADC. Assume that the ADCs are all Flash ADCs and see how this might be implemented. So this is 2 bits. Now remember, this is ADC 1. This will be sampling the input in one clock phase. Say it is sampling the input in clock phase phi 1. So it will provide the final digital output in phi 2. Maybe I'll write it other way. This is the sampling phase. This is the comparison phase. It's sampling the input in phi 1, comparing it in phi 2. Now remember, the amplifier you have here, it is taking the difference between the input and the DAC output and amplifying it, right? So let's see with respect to the input what should happen. So if the first ADC is sampling the input in clock phase phi 1, in which clock phase do you think the amplifier should sample the input? This is what we are looking at. I know this input is getting sampled in the ADC at phi 1. So in which clock phase the amplifier should sample the input? Phi 1? Why not phi 2? Yeah, remember that the idea here is to try to cancel the quantization noise. So if the first ADC is sampling the input in phi 1, to get the same action you have to sample here also in phi 1. Only then you will also be sampling the same input. So you sample in phi 1. So in which phase you can amplify it then? We can amplify in phi 2. So what kind of circuit does this? The switch capacitor amplifier, and delayed or delayed free? Delayed, right? Here I am sampling in phi 1 and doing in phi 2. And remember, the gain with respect to the input is positive. So you need to have positive gain. And the delayed amplifier has a positive gain. So let's quickly draw the circuit. So let us say this is what we have. Yeah, I'll come to that next. You are absolutely right. Yeah. So in phi 1 you sample the input. In phi 2 basically transfer the charge to a feedback capacitor. And remember, this capacitor has to be reset so that you start fresh. And let us say you reset it this way. Fine. In clock phase phi 1, capacitor C2 is reset and it works as before. Fine. And what will be the gain here? C1 by C2, C2 by C1. Remember how the circuit operates. It's sampling a charge of C1 times V in. C1 times V in goes here. So voltage is C1 by C2 and here it is plus C1 by C2. Right? So this is something you can do. Now let's come back. Let us say this is the DAC output. Now the first ADC is comparing and giving a digital data in phi 2. So the input to the DAC is available only in phi 2. Let us say the DAC has no delay. So the earliest the output can come here is in which clock phase? Phi 2. The DAC has no delay. Let's say that is doable. Only in phi 2 the DAC output is available. So in which clock phase the amplifier should sample the DAC? In phi 2. Phi 2 is when the data is available. So you will have to sample in phi 2. So with respect to the DAC, you sample in phi 2 and you amplify it in same phase phi 2. And remember, the gain should be positive or negative for the DAC. Negative. And how do you do this? The delay free switch capacitor integrator, because you are sampling and amplifying in the same clock phase. So maybe I'll draw it first separately and then we'll see how we can do it together. So remember that in clock phase phi 1 I am resetting the capacitor. In clock phase phi 1 this is getting reset, sorry. This is not going. Okay. So in clock phase phi 1 this is getting reset. In clock phase phi 2 I will feed in the MDAC here. So here I will get a gain of minus this, right? So the first circuit will give me an output C1 by C2 times Y. Second circuit will give me minus C1 by C2 times MDAC. I want C1 by C2 into Y minus MDAC. So what can you do? Yeah, I mean now you see that the two circuits, if you stare at them, it looks like I have done superposition. So here I have grounded this input. In the first circuit I basically grounded this. So to get the same, I mean to get the sum of these two, you do use superposition. So you basically apply. So, and if you do this, the output here is this. Fine. So now at least we know how to make the amplifier. So let me copy this. We'll reduce it slightly. Why is this not going? Yeah, okay. Cool. So now we know how to make the amplifier. Next thing pending is to see how to make the DAC. Right, and let's take a 2-bit case. Let's assume the first ADC is 2 bits and see how we can make a 2-bit DAC. So first ADC is 2 bits. Let us take a single-ended case for example. You can extend it for a differential case. Range is 0 to Vref. What is the step size delta? Vref by 2 power 2, which is 4. Fine. And I have a 2-bit Flash ADC. How many comparators I will be using? 3 comparators. I mean, let's not assume we are using that 1.5 bit stage. For simplicity, let's go with this 2-bit case. So I'll have 3 comparators. So how many thermometric bits I'll have? 3. Each comparator output is 1 thermometric bit. Let us say these are the 3 bits V1 ABC. If the digital code is 0, all of them will be 0. If the digital code is 1, one of them is 1. If the digital code is 2, what will happen? Fine. Now let us say this is the step size delta and the digital code is K. So if the digital code is K and step size is delta, what might be the DAC output for a code K? If the digital code is K, now we are looking at a DAC. Let us say the input digital code for the DAC is K and step size for the quantizer is delta. What might be the output of the DAC? Yeah, right. Which means if the code is 0, I'll get an output of 0. If the code is 1, I'll have Vref by 4. Here it is 2 Vref by 4. This is one simple way in which you can make the DAC. So let's see how you can implement it on circuit. Now let us say, let me take an example. Let us say we are in this range. The input code is 1. So the output should be Vref by 4. So at the amplifier output, I should have the input minus the DAC output times the gain. Okay. Now remember that I just have a voltage of Vref in my circuit and I want to generate all these voltages using here itself, right? So which means I can either connect this point to Vref or to ground, that's all. I don't have any other small voltages. If you go and connect this to Vref, what will be the output? C1 by C2 into y minus Vref, but that's not what you want. You wanted basically Vref by 4. So to start with, let's even assume that the y is not there. Okay. So this is what you have, but what you want is minus C1 by C2 into 1/4 of Vref. What can I change in the circuit so that the output reduces by a factor of 4? C2, or what? I can reduce C1 by, if I do C1 by 4, I get this, fine. But now if I go and connect this to the input, what will happen? Yeah, I'll get basically, right now it is this. So this is something that you want, you got it. But with respect to the input, you got C1 by C2 into y by 4. Right? But what you want is y times C1 by C2 minus Vref by 4 into C1 by C2, right? This term you got it correctly, whereas this term you are not fully there, you are 1/4 there. So now think about it. I have one switch capacitor branch with C1 by 4, sampling the input and feeding the charge. That is giving me 1/4 of what I want. I want 4/4, that is 1. So what should I do here? If I have 4 parallel branches, each of them having a capacitance of C1 by 4, and if they also sample the input and transfer the charge, we are set. Which one? Oh, you use this way.
The input is the input is 4y.
Yeah, that's what. If you, yeah, but again, you can do this, but which means for this you need to have another amplifier. Right? In a simpler case is to do this. So what I'll do is, just like I have one branch here, now I'll have how many extra branches? 3 extra branches, and these branches will only process the input, not the DAC output. Because with respect to Vref, we got what we want from this guy. Okay. So let me see if I can draw all 4. Maybe I'll reduce this size. So let us say this is second branch. This is ground. Third branch and fourth branch. So all of them will sample the input and transfer the sample charge to the feedback capacitor like this. You can think about it. The first branch is sampling y minus Vref. The charge is y minus Vref times C1 by 4. Second branch is only sampling y times Vref by 4, y times Vref by 4, y times C1 by 4, y times C1 by 4. So the total charge that is pushed into this is 4 times y into C1 by 4 minus Vref into C1 by 4. This is the total charge getting pushed by C2, that's what it is. Okay. So this is clean. So now let us say you want to have a case this, let us say the case is now this, you need to generate 2 Vref by 4. How will you change the circuit? Right now only one branch is sampling Vref. If you want to have 2 Vref, 2 of them will be Vref, other 2 will be ground. If you want to have 3 Vref, 3 of them will be connected to Vref, this is connected to ground. So one thing is clear, this guy is always connected to ground, right? You just need to make sure, depending on the 3 bits here, you go and control these 3 branches and connect this node either to Vref or to ground. Fine. So if the thermometric bit is 1, you connect it to Vref, otherwise you connect it to ground. So again, that you can do it like this. So you'll have 2 switches, one to Vref, one to ground. You will connect the switch to Vref if, let us say, thermometric bit D1A is 1, otherwise it's ground. Same thing here, it's connected to Vref if the second thermometric bit is 1, otherwise it is 0. Here again the same thing, it is connected to Vref if the third thermometric bit is 1. So this way you see that we have this portion acting as the DAC, and the input is sampled here, and we are taking the difference and multiplying all in one circuit. Okay. So this is basically for a 2-bit case. Now we can easily generalize. Let us say you want to have a B1 bit DAC. Okay. Here is this. So how many thermometric bits will have? 2 power B1. Okay. Now when I had a 2-bit case, the capacitor was C1 by 4. Now what should this be? C1 by 2 power B1. Okay. So same thing, I'll just quickly change. And when I had a 2-bit, I had total of 4 branches, of which 3 of them were controlled by the thermometric bits. Now I have B1 bits. So total of how many branches I should have? 2 power B1 branches, and of them how many branches will be controlled by the thermometric bits? 2 power B1 minus 1. Okay, so what I'll do, I'll assume that this is there, and here I'll put dot dot dot. And let us say totally you have 2 power B1 branches, and of which 2 power B1 minus 1 branches are controlled by the thermometric bits. Correct. This is one circuit that is basically doing 2 jobs. It is acting like a DAC and also amplifying the difference between the input and the DAC output. So commonly this is called as the multiplying DAC. Or often abbreviated as M-DAC. Again, this circuit implementation is in particular to a Flash ADC. If the first ADC was a Flash ADC, then only you will have this thermometric bits, then this kind of.
It is basically that T junction where we are getting the DAC in output and the input we are getting. The pipeline ADC, the ADC one was there.
Yeah. So this entire thing is now one circuit. Right? So let me draw that probably in a more realistic way. So if I draw the pipeline ADC block diagram, I obviously have the first stage. This is ADC1. Okay. Now I know that DAC subtraction amplification is all done in one circuit. Let us say it is giving the thermometric bits here. So this goes to M-DAC1. That has the gain also, and then you give it to the second ADC, and let us say the first ADC samples in phi 1, compares in phi 2. The M-DAC should sample the input in which clock phase? The same input should be sampled here also, so the output will be available in phi 2. So if the signal here is available in phi 2, in which phase the second ADC should sample? In phi 1 or 2? Phi 2. Because phi 2 is when the signal is available, you sample it here. So in phi 1 is when it will compare and give the output. Again, if I were to draw one more stage, so this is again a thermometric bit. So give it to the second M-DAC. And then let's say you have a third ADC finally. So this guy is providing the compared output, the digital output in phi 1, right? And it is sampling the input in phi 2. So in which phase this one should sample? Should sample the same signal, so do in phi 2. So output will be available in phi 1. So this should sample in till given phi 2. This is how the timing will look like. So as you see, right, the first ADC is giving the digital data in clock phase phi 2. The second ADC is giving in the next clock phase phi 1. So you have essentially half clock cycle of delay. Same thing here, if this is giving in phi 1, only next clock phase phi 2, the next ADC is providing the digital data. So you have a delay of Ts by 2 here also. So which means finally if I'll have to recombine the digital bits as this, right? V1, how do I recombine if the gains here are G1 and G2? How do I recombine the data? If the gain is G1 and G2 here, plus. So when I reconstruct this, I should make sure that, remember the third ADC is giving data at some time instant, but the first ADC would have given the output 1 clock cycle before. So this should be basically delayed by 1 clock cycle. I'll say 2 times Ts by 2 delayed, and this should be delayed by 1 Ts by 2 delay. That's after delaying them is where we should add it. Okay. Huh? You understand that when the third ADC is giving, let us say, a data, the corresponding data from the first ADC would have gotten 1 clock cycle before. So when you are doing this reconstruction, you should basically delay each of the ADC outputs so that each ADC output is corresponding to one particular input. And in practice, we do one more modification in the implementation. See here, right? You see that the input is sampled both in the ADC and the M-DAC. So let us say I draw it here. This is the first ADC. This is the, let us say, M-DAC. So the clock phi 1, let us say, goes here and goes here. Physically, they will be placed apart. So which means the clock reaching the first ADC and the clock reaching the M-DAC, will they be identical or will there be any difference? There will be a slight delay. So which means the signal sampled by the ADC and the M-DAC, that will be different. So that will again corrupt the entire business, and that's happening because I'm sampling the input locally in each of the blocks. So what might be a solution to this? You kind of sample it globally and feed only the held signal. This is something we saw in the Flash ADC also. What we have is a global sample and hold, so that the output of the sample and hold is a held signal like this. So which means even if the sampling instants are staggered, you are okay. So if I were to modify this, a more practical thing or a conventional approach is to have a global sample and hold.